Hello everyone, today we will be talking about the beginnings of perception. This is our chapter 2 discussion for the semester, and today we will begin by discussing some very particular key questions or key issues that we have associated with the field of perception. And today's discussion we're going to talk about the following issues. Number one, how are psychological processes involved in perception? And number two, how can electrical signals in the nervous system represent objects in the environment? So before we begin discussing these two particular questions, we first have to begin to understand first what the perceptual process is in terms of the field of perception. Now, our discussion last week, or the video lecture that I had posted on YouTube for you last week, essentially went through and discussed what the process is for the perceptual process in terms of the sequence of events. But here, just to kind of reiterate that issue, let me just quickly mention that. The perceptual process is really divided up into four different categories. The four categories are the following. Number one, we have our stimulus. Our stimulus is whatever the physical element is in the world that we are trying to observe with our eyes, taste with our tongue, smell with our nose, feel with our hands or with our body, with our sensations, and also hear with our ears. So whatever that physical element is out there in the world, that's what we're trying to process at this point. So the idea of the perceptual process is really there just to determine our experiences, have a reaction to the information from the environment, and then be able to continue on down that line. Now, after it is that we have that stimulus existing out in the physical world, once it lands on our sensory system, whatever that sensory system may be, we now need to convert those physical properties being given off by that stimulus. We need to convert them into electricity. So within the process of electricity, we have what we call transduction of information and transmission of information. With transduction of information, that is where we essentially convert physical properties of the stimulus and convert that into electrical impulses. And we do that by having our receptors on our sensory systems be able to translate that information for us. And then we have transmission of information. And this normally happens by when it is that we have activation of our receptor cell on our sensory system, being able to now have action potentials that travel through neurons all the way to our brain for processing. Now, once it is that we have transmission of those electrical impulses to our brain, within our brain, we should be able to extract existing information, or what we would call experience, based on our previous knowledge. And then we also have action. And the action is whatever it is that we're going to perform in terms of adapting to that stimulus that's existing, or that we have to have some type of response to that stimulus that exists out there in the world. And then last, we create knowledge, or what we also call memories. So that way they then become the previous experiences that we have in step number 3. So we continuously go through this process every second of our day, that we're processing information consciously from our world. Now, in terms of our brain, once it is that we actually send those electrical impulses to our brain is really made up of two hemispheres, what we call our right and our left hemispheres. Our right and our left hemispheres are connected by what we call our corpus callosum. Our corpus callosum is this band of fibers that connects both the left and the right hemisphere and allows for communication to exist between them, so for coordination purposes as well. And essentially here with our brain, we essentially have what we call modular organization. And what modular organization means is that we have sensory modalities that have primary receiving areas. So think of, for instance, your computer. Within your computer, you're going to have primary receiving areas. So think about, for instance, going to the icon of My Computer, on your PC, right? Or on the drive for your Mac. And then within that drive, you're going to have subfolders. Those subfolders are going to be a module, or they're going to have this idea of a sensory modality that only particular information is going to be stored within those areas. So we would assume that that kind of exists also within our brain. Thus, that, for instance, when we're looking at aspects associated with vision, we look at our occipital lobe. When we talk about audition with sounds, we talk about our temporal lobe. And when we talk about tactile senses, so here our touch and our feeling and our temperature changes, we're talking about our parietal lobe. So here we do definitely see this modular aspect associated with primary receiving areas for our brain, but it's not necessarily 100% straightforward as we would assume here. So just because we say that we do have these sensory modality primary receiving areas, it doesn't mean that vision is only in the occipital lobe. That's the primary receiving area. But there still may be some activation of our parietal lobe, our temporal lobe, or even our frontal lobe whenever it is that we have visual stimuli. So think of it again like having a file that's stored within one particular folder on your flash drive or on your computer, but then you also have another similar file stored in another folder on your computer as well. It may not be the same one, but they both might come up if you were searching for a document. So they may have similar titles or they may have similar content, and that's thus why they both might come up in a search. So here we do definitely have to think about that it's not 100% modular, but rather there may be some cross-activation that may exist between them, and we'll talk a little bit about that in just a couple of seconds here. So just so that way we can see where it is that we're talking about our distribution of our lobes in our brain, this is what it would look like on our left hemisphere. In our right hemisphere, we would have an exact mirror image of this. So we do have what's called symmetry in our brain. So we have mirror images of the left and the right hemisphere on both sides of the brain. Our parietal lobe, as you can see, is towards the top part of your brain. This is where we actually have our skin or our tactile senses. Our frontal lobe towards the front of the brain, very creatively named here. That's much more important in terms of working aspects associated with memory and also aspects associated with personality, like we've seen with cases such as Phineas Gage, for those of you who remember that from personality psychology or from psychobio, or also from Intro to Psychology. They talk about Phineas Gage, that he had damage to his frontal lobe. So we think it's very important for personality aspects, also very important for judgments and decision-making skills, seem to be very important in terms of the frontal lobe. Now you'll also see the occipital lobe, which is towards the back of our brain. Our occipital lobe, very creatively designed to have been in the back of our brain. It's very important that it's there, even though it's very far away from where our eyes would be. Our eyes would be here on the left-hand side of the screen. Our occipital lobe is towards the back. Since our world is primarily based on visual processing, it's going to be very important for us to be able to protect that as much. So if you were going to be able to have damage on a specific area of your brain, more likely it's going to happen in terms of the front of the brain or towards the sides of the brain or towards the sides of your head, not necessarily towards the back. So we try to do protect as much as we can in visual processing. So when you think about it from an evolutionary standpoint, we've evolved quite creatively to be able to protect that as much as we can, since the primary aspects of our world in terms of our senses is really based on vision. Now you'll also see the temporal lobe, which is going to be right above your ear. So your ear is going to be right about here. We do see that the temporal lobe is very close to your ear, and that again is going to be very important for the processing of sounds as a whole, not just language, but sounds in any capacity. Now, when we look at the aspect of the frontal lobe, like I was mentioning, the aspects of Phineas Gage, or the case of Phineas Gage, we find that the frontal lobe is very, very important for the aspects associated with reward, attention, planning, personal drive. Personality seems to be a big issue there that we do see being controlled by the frontal lobe or being a part of the frontal lobe, and also in terms of making judgments and decisions in terms of our everyday planning or in terms of our everyday skills seem to be very important for our frontal lobe. Now, for our other lobes of the brain, we do see the parietal lobe, and also the parietal lobe is split up into two different parts, what we call the left parietal lobe and the right parietal lobe, depending on your hemisphere. The left parietal lobe, we do see quite a bit in terms of processing associated with tactile senses, with spatial senses, and also navigation. Now, we do find that there are some problems that exist in some individuals with parietal lobe damage, that they may have right-left confusion, they may have difficulties in writing or even mathematics or even in object recognition. So that seems to be a big issue that we sometimes find with parietal lobe damage, especially in the left parietal lobe. In the right parietal lobe, if there is damage, sometimes we actually see what's called contralateral neglect or visual neglect that we sometimes see, that where essentially a person may neglect a part of the body or a part of space based on the damage that they actually receive to the parietal lobe. And again, here the parietal lobe is also going to be very, very important for us in terms of processing of any tactile responses that we actually see. So in terms of vibrations, in terms of temperature, in terms of recognizing objects with our hands or with our sensory skin processing abilities are going to really be processed in the parietal lobe. In our temporal lobe, we see that the temporal lobe is going to be very important for aspects associated with word recognition, with facial recollection as well. There are some aspects associated with memory that are very important for the temporal lobe, and also for the processing of sounds, especially for the processing of speech. Within our temporal lobe, we actually have two very important areas for the processing of language. which we call Wernicke's area and also Broca's area. Broca's area is very important for the production of language, while Wernicke's area, and that's Wernicke's with a W, is very important also for the processing of comprehension. So we actually see that there are some individuals who have some type of damage to either Broca's area or Wernicke's area, which we have them named as Broca's aphasia or Wernicke's aphasia, and individuals who suffer from Broca's aphasia tend to have trouble producing words, while people who have Wernicke's aphasia have trouble understanding language. And here later on in the semester, when we talk a little bit more about sounds and hearing, we'll talk a little bit about that aspect associated with language. So now, as you see, in terms of our discussion associated with the three lobes up to this point that we've talked about, the frontal lobe, the parietal lobe, and also the temporal lobe, you'll see that we also have different aspects associated with different processing skills. So for instance, here in the temporal lobe, we still have aspects associated with facial recognition, even though this is not the occipital lobe, that we would say that this is the primary area for visual processing. But yet we do still have some visual processing occurring. Now, as I also mentioned, memory seems to be a big part here in terms of the temporal lobe. We see the very famous case of H.M. as being a big factor in terms of his behavior that he demonstrated was because he had some damage also to the temporal lobe in this particular case. Now, our final lobe that we'll talk about here is the aspect of the occipital lobe. As I mentioned before, its primary processing purpose is for visual processing of information. We do also see that there may be some function loss associated with the occipital lobe, and in those particular cases, we may see anything from individuals going blind to color blindness to what we also call field cuts. We also see visual hallucinations and illusions are actually processed quite primarily from the occipital lobe. Now, a big question that always comes about is the following. How is it that the two hemispheres communicate between each other? So if we have this band of fibers that connects the left and the right hemisphere, how is it that they communicate with each other? And the process by which they communicate with each other is what we would call our neurons. Our neurons are these essentially cables that we have that connect our receptor sites from our sensory system, and they connect all the way to our brain. So essentially here, think of it like a cable that goes from the TV source that you have coming in from the street that goes all the way into your TV. So it's receiving the signal coming in from the street, and that cable sends that information through all the way to your TV for processing of information here. So ultimately here, our neurons are essentially going to be these fibers that are always transmitting impulses, and here the impulses that we're talking about is essentially those electrical impulses. So at the primary receiving areas that we have in terms of your brain, their purpose is to process the information based on the experiences that we've already had and also the new experiences that we're creating in terms of the new knowledge and the new memories. But whenever it is that we receive the signal from the sensory receptor site in terms of your hands, your eyes, your tongue, your nose, or your ears, when you receive those physical properties from the stimulus that are existing in the world, we have to transduce that information and create those electrical impulses and then transmit that information to the brain for processing and then back to your extremities, so that way you can have actions in any capacity, or your eyes so you can move your eyes around and scan the scene. So now, in terms of our neuron, what are our neurons made up of? Our neurons are actually made up of four parts. They're made up of what we call our dendrite, our axon, our terminal button, or what we also call our terminal bouton, if you want to use the fancy word for it. And we also have what's called our synapse. Now, our dendrite essentially functions as an in coming from the receptor. So as the receptor is going to be connected to these neurons. The neurons have to capture the information coming from either the receptor or from other neurons. So here in a moment, I'll show you a graphical representation of our neuron to demonstrate how it is that they actually communicate with each other. But here, our dendrite is receiving the information in, and it's receiving that information from other neurons or also from the primary receptor site associated with your sensory system. Now, the axon functions as an outsource. So it essentially functions as the cable that transmits the information from one neuron to the next neuron. Now, since it's going to be transmitting that information from the cell body to another neuron, part of that electrical energy that's being transmitted needs to be covered in a very important protective insulation, or what we would call this fatty insulation called the myelin sheath. Now, the purpose of this myelin sheath is essentially to insulate the axon so as to keep the electrical impulses and the electrical energy inside of the axon. So think of it as insulation in your home. Inside the walls, you have to have that insulation. If you don't have that insulation, any energy that you keep inside of your home, such as heat or coolness that we have from our air conditioner or from our heater, essentially is going to get dissipated out through the walls, and you're going to lose that energy. So the same thing happens here with our axons. We have to keep them insulated so that way when those electrical energy, that electrical charge goes through, it stays within the axon and it doesn't get lost. This is why some individuals who suffer from multiple sclerosis, or what we call MS, actually have trouble controlling some parts of their body because those electrical impulses are not sent correctly from neuron to neuron. Thus, the electrical impulses get lost. And essentially think of those electrical impulses as carrying the information, because that's what they do. They carry the information from one point to the next and essentially send that message on through to the next neuron, to the next dendrite at the terminal Bouton stage. So at the end of the axon, we actually have a release of chemicals by our terminal Boutons. Essentially, we have the release of chemicals that we call neurotransmitters. And essentially, these neurotransmitters go into the synapse, which is going to be the synaptic cleft, or this gap that we have between adjacent neurons. So whenever it is that these neurotransmitters, these chemicals get released from one neuron to the next, they essentially function like a lock and key mechanism. So it's going to be very important for us that whenever it is that we do see the release of that neurotransmitter from one point to the next, we do definitely have to understand that it's not always going to turn on the next neuron, because sometimes the message that it's going to send is do not send this message through, or send this message through. Or if it's sometimes going to send the message through, but if we're taking a specific drug, for instance, that inhibits the processing of those neurotransmitters, it may not be able to send that message through accurately to the next neuron. Later on in the semester, when we do talk a little bit about drugs and behavior, I'll definitely bring this issue up again as to how it is that we sometimes block those keys into the locking mechanism of the next neuron. So when we see here our graphical representation of our neuron, this is essentially what we have: billions upon billions of these neurons within our body. We have all of these fibers. On the left-hand side, what you'll see here is you have your receptor sites, which are going to be your dendrites. So imagine here that we have another dendrite that's coming in, and we have here an axon our terminal Bouton that we have here that's coming out from our axon. So here's our axon. We have our terminal Boutons that are at the end of our axon. And from here, we're going to have the release of that neurochemical, or that neurotransmitter, being released from this terminal Bouton to being captured now by the next dendrite. Okay, very, very important. Now, our cell body here is going to be the life support system of our neuron. So if our life support system dies, our neuron will die. So it's going to be very, very important for us to being able to have the cell alive as much as possible. This is why we do not want to kill off any of our neurons, let that be through damage or through drug use or any other factor that might potentially contribute to the loss of neurons in the future. Now you'll see here, as the impulse is coming in from the dendrite, it'll activate the cell body to tell that the axon, you are going to now send a message through it or not. If the cell body does not turn on based on the information that's being received by the dendrite, it now knows not to send that information through, or to continue sending that information through, depending on whatever the case may be. And you'll see here that the axon is covered in that nice myelin sheath, meaning that we will have that electrical impulse maintained within the axon until it receives the message at the terminal Bouton, where it's going to release that neurotransmitter. Now, when we think of that electrical impulse that's being created by the cell body, we're essentially here talking about what we call an action potential. And an action potential is going to exist whenever it is that we have a neuron that is inactive, or it has what we call a negative charge because it's at a resting potential or at a resting state, meaning it's not turned on at that point, to now becoming active, or now having an energy potential that now crosses the membrane, and it creates what we now call this action potential. So we see here on the left-hand side our negative charge, or what we call our resting potential. Once it is that we receive information from the dendrite or from the sensory system at the receptor site, that's now being given to the dendrite, to the cell body, saying yes, send that signal through to the next neuron, send that signal through the axon so it can be received at the terminal Bouton and release that neurotransmitter. We will have an action potential occur where we have a negative state where we don't have the neuron being turned on, to having an active state or an action potential state where now it sends that information through to the next neuron. Now, again, going back to this issue of where all of this is happening and how fast this is happening, we are talking about the release of the neurotransmitters. Once the action potential occurs here, that we send the signal through, now we send the signal from this neuron through our neurotransmitter through this idea of having this chemical being released at the terminal Bouton state, and thus sending that signal on through to the next to the next neuron, so it can potentially create an action potential or not. So there's no guarantee that that will actually happen in the future or not at the next neuron, depending on the message that's being sent through. Now, in terms of our action potentials, there's very, very important properties associated with action potentials. And one thing that we have to consider about an action potential is that all action potentials remain the exact same size. The only thing that differs between the strength of a physical stimulus and the action potential is that if the physical stimulus gets stronger, that just means the action potential fires more. It doesn't mean that it fires stronger, it just means it fires at a more intense rate. And that's very, very important for us to understand, that we don't actually see a change in the action potential size, but rather in how many times the action potential actually occurs for that particular neuron. Now here I mentioned that the size or the energy, the physical properties associated with the stimulus are getting stronger. So assume, for instance, here that you're talking about a person talking normally to a person screaming. As the person talks louder and louder and louder, that physical stimulus is getting stronger in terms of its physical properties. Here, the action potential has to interpret that information. It doesn't say I'm going to fire stronger now. It just says I'm going to fire more times. The firing of more times of the neuron means that the stimulus is actually getting stronger in this particular case. Now, our refractory period does exist within an action potential or within a neuron, meaning that once a neuron fires, it has to rest for a given period of time, and then it has now the ability to fire again. So imagine it as being when you click a pin. When you click a pin once and then you click the pin again, there's that break in time in between when it is that you can use the pin again and again. The same thing is happening here for an action potential for a neuron. It fires once, so you press the button, and now you press the button again to tell it to now take a break, to rest, but then there has to be this time in between where it's not going to be allowed to have another click or another action potential exist because it has to recharge its batteries in that instance. Now, we do see something that's very interesting in terms of action potentials. In terms of action potentials, we actually have what's called spontaneous activity. And with spontaneous activity, this actually means that we actually see activation of a neuron occurring sometimes without actual physical stimulation from a physical stimulus. And this is actually what we think happens quite frequently with dreams in some particular instances, that some information is just becoming active even though there is no physical properties or physical stimulation existing there in that particular stimulus. Now, again, just to kind of reiterate this idea of a physical property the physical stimulus getting stronger, if we go from A to B to C, you'll see that now the physical stimulus that exists out there in the world is getting stronger. Okay, and how do we know this? Because the firing rate of the neuron is getting faster and faster and faster. So you'll notice it's always the same size in terms of an action potential, because action potentials are all or none. It can't have half an action potential exist. It either fires or doesn't fire. If it fires, it always fires at its maximum amplitude, but in terms of its frequency, in terms of how often it happens, it's going to be based on the physical stimulus that exists out there in our world. So here in our particular instance, having soft stimulation versus having medium stimulation versus having very strong stimulation. So we'll just see here that we actually have the action potential occur more and more and more. Now, the next thing that we're going to talk about here is the aspect of the synaptic transmission of information from one neuron to the next. And how does this happen? Again, this happens through what we call our neurotransmitters. The neurotransmitters are actually released at the presynaptic neuron from the vesicle, and they're actually received at the postsynaptic neuron at the receptor site at the next dendrite. So here, these exist like a lock and key mechanism. So they have to match from one to the next. So they have to match from the presynaptic neuron to the postsynaptic neuron, and if they don't match, or the postsynaptic neuron is blocked at the receptor site for whatever the reason may be, the information may not get transmitted through. So think about it in terms of a pain medication. Pain medications essentially block off the ability for a neuron to process information saying, I am in pain. So the signal is sending through saying pain, 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 but the drug comes in and blocks off at the receptor site, not allowing that presynaptic message of that neurotransmitter sending through saying, I am in pain. It's blocked off at the postsynaptic area, thus indicating now that there is no more pain because that message is no longer being sent through. So here, from the postsynaptic neuron to the from the presynaptic neuron to the postsynaptic neuron, we have to have those release of those neurotransmitters being sent through. Now, in other classes, you all will learn, especially, for instance, if you guys take psychobio or physiological psychology, you'll learn about reuptake of neurotransmitters in some particular cases, that the neurotransmitters then get released from the receptor site and they get taken back up by the previous presynaptic neuron area, so that way they can be reused again in the future. And in other instances, you will not have reuptake, and the receptor site just absorbs that chemical and diffuses it, so that way it can be then used as energy in the next neuron if needed. So again, with the idea of our synaptic transmission, ultimately what we're having here is we're having the release of that information from the presynapse to the postsynaptic area. And again here, they either do get absorbed in, or they actually do fall into the receptor site, or they do not, depending if it's blocked or if it doesn't have the right size in that particular area. Now, some of the neurons that we actually have, or in terms of some of the neurotransmitters that we actually have within the presynaptic area that get released to the postsynaptic area from the neuron, can either take two forms. Number one, they can become excitatory, or number two, they can be inhibitory. In terms of excitatory transmitters, or in terms of excitatory neurotransmitters, these cause depolarization, ultimately making the neuron become much more positive, increasing the likelihood of an action potential to exist. Versus an inhibitory neurotransmitter, which causes hyperpolarization, meaning that the neuron becomes more negative, which decreases the likelihood of an action potential existing in the future. So again, these are the two forms that we can actually have in terms of our neurotransmitters. Now, going back to the sensory system, and going back to the point at which the sensory system begins to process information from what we would call our receptive field, or our receptive factor in that particular area at that point, we're going to use the eye as an example here for the discussion of receptive fields. So in the area of the eye, for instance, and the area of the retina, this actually affects the firing rate of a given neuron in that particular circuit. So if you look here at how A, B, and C on the left-hand side of your figure are displayed versus how A, B, and C are actually displayed here on your retina, you'll see that our receptive fields don't necessarily match up in a linear fashion. So here, it's very important for us to understand that the way that we always have assumed that the way our world works is not really the way our world works, because we actually see that there is scientific evidence that suggests that there are differences in the way that we process information. But yet, our brain interprets it in the fashion that we assume our world works, which is very important for us to understand. And in classes like cognitive psychology, you'll talk much more about that kind of relationship that you'll see there. So in terms of our receptive fields, these are going to be used by monitoring single cell responses. So ultimately what that means is that we as researchers have looked at these one single cell responses and looked at them as being our receptive fields. So whenever a stimulus is actually presented to the retina, we measure the response in an electrode of that cell to be able to identify if that receptive field is being active or not. Now, with our receptive fields, we actually see a very interesting pattern emerge with receptive fields. Receptive fields have what are called center-surround receptive fields, which essentially mean that there are excitatory and inhibitory effects that are found in our receptive fields. Meaning that if a physical stimulus, in this particular case, an object that's out there in the world that our eye is landing on, or that's landing on a particular area of the retina on our eye, or that we've put our eye on that specific object in our world, depending on where the object lands on that receptive field, it may have an inhibitory or an excitatory response. So here in our particular case, if we have what we call the center-surround receptive fields, the center part is going to be excitatory, while the surround part is going to be inhibitory in this particular case. Now, we also do see that there are the opposite, in which we call inhibitory center and excitatory surround. So depending on which type of receptive field it is that you have, that's ultimately going to make the determination of how it is that we're going to perceive what that object is based on the responses of the receptive fields. Now, you'll see here that once it is that we actually have the object landing on our center surround receptive field, and we have our inhibitory surround in this particular case, you'll see that if the object lands on, let's say for instance, A, which is going to be on the outside of the receptive field, you'll have just the spontaneous activity of the neuron existing. This is why we have just some of that brief activation that's occurring by our neuron. Now, if we look at B, now you'll notice that if the object lands on B, you'll start having more of that firing rate existing on your neuron because more of B is taken up. So now imagine if the object is landing on B, but it only lands on B and it takes up all of B's receptive area right here. So the object only lands on B, but it takes up all of B. That means that this response by that neuron is going to get stronger and stronger and stronger. Not higher in amplitude, but it just means it's going to get more frequent. Again, relating back to the issue of having an increased intensity of firing rate of our neuron, not amplitude-wise. Now, if our object lands more on C than it does on A or B, you'll notice that we do have some activation occur, but we don't have that much activation occur. So the stimulus lands on C in this particular point. It lands here when it's on, but there's no activity because it's telling it to be inhibited at this point. Now, the reason that this is so important for us, again, is because now what's existing for us is that depending on how much of an area is being taken up by the excitatory center or the inhibitory surround, this is ultimately going to create the pattern of firing rate for that particular neuron based on that particular receptor's receptive field. And that's going to be very important for us because one thing that we do definitely find is that we find that based on the pattern of activity is how it is that we actually interpret information. So in other words, it's not that just one single neuron, one fiber is becoming active whenever it is that we see something out there in the world, or that we hear something, or we taste or smell or feel something out there in the world, but rather billions and millions upon billions of neurons are becoming active based on our sensory system's activation of the receptor and its receptive field, thus meaning that we're going to have all of these neurons turning on and sending different signals. Based on all the different signals that are being sent by each one of the neurons, once it is that they reach the brain for interpretation, the brain's job now is to interpret all of that information that's coming in from the neurons and ultimately creating what it is that we say that is that particular object out there in the field. So in the case of, for instance, our cat here, if we have a light that's being shown right here on point A and it lands on, let's say, 5 different receptive fields, those 5 different receptive fields are going to activate multiple neurons. Those multiple neurons are all going to have different firing rates that we would see here, for instance, right? They're all going to have all these different firing rates, and the pattern of the firing rates across all of those neurons are going to give the cat the interpretation of whatever that object is in that specific environment that they are working in at that particular point. So it's very important for us to understand that it's not just one single fiber, but millions upon billions of fibers that are working all together to create the perception of what it is that we have out there in the world. Now, we also do see this in terms of other species as well. In terms of primates, for instance, on monkeys, we actually see that the thalamus shows the cells that respond to center surround receptive fields as well. In other words, indicating that, that monkeys and primates are very good models for us to being able to use in terms of our understanding of how receptive fields work as a whole. Now, very interestingly, one big issue that always continues to come up within the field of sensation and perception and cognitive psychology as a whole is the issue of representation of the environment and how we have neurons within our neurons that are connected to our brains in terms of our interpretation of what that world is. So again, going back to this idea of, do we only have one specific neuron or do we have multiple neurons that are ultimately going to create the message? It's really more of the distributed aspect, that we have multiple neurons that are providing all pieces of information to the puzzle, and then together they create whatever it is that we're experiencing out there in the world. Not that we have specifically one neuron that indicates exactly what it is. So in other words, let's take, for example, the differences between, sorry about that, guys. Let's say that we were looking at the differences between, give me one second, there we go. The differences between different Halle Berrys that we see, right? So a picture of Halle Berry as she's walking down the red carpet versus Halle Berry as Catwoman versus the words Halle Berry. According to what we would call the grandmother cell hypothesis, we would only have one single neuron that would respond to all Halle Berrys, no matter how Halle Berry changed. When in reality, that would be very unlikely that that would ever happen. But rather what we would have is probably this idea of a non-specific coding. In other words, that we have multiple neurons all coexisting and working together to create the idea of what Halle Berry is. So in other words, they all share similar features, and since we take multiple features from each one of the images that were being presented, we can then come to the conclusion that they're all Halle Berry. Not necessarily that we have this idea of specificity coding, that we only have one single neuron that responds to one specific stimulus out in our world. So the idea with specificity coding, to be honest, is a big problem with it. That number one, that would mean that there would be too many different stimuli out there in the world, or there would be too many different stimuli that exist out there in the world to assign specific neurons to work towards. And since there would be too many neurons for us to consider, it would mean that we would have this impossible number of neurons for all of the things that exist out there in the world. And what happens if there's just small variations in between each one of them? So let's say, for instance, so again, we look at the picture of Halle Berry, but Halle Berry isn't using those hooped earrings, but rather she's using diamond-studded earrings. So here, according to the specificity coding hypothesis, I would have to have a brand new neuron that looks at Halle Berry just in that specific fashion, and it would be able to say I would have to have one specific neuron just for that. But here again, that would be too difficult. But rather with the distributed coding idea, or the distributed coding hypothesis, again, we use the pattern of firing of all the neurons to say, are there similarities across all three in this particular case? Are there similarities across all three of these images that ultimately indicate that they would be the same, thus leading us to the idea of who Halle Berry is, and not needing that many neurons to be able to process a very large number of stimuli that we would have. So again, going back to this idea of specificity coding versus non-specificity coding, or the distributed coding aspect, specificity coding would suggest that if we would have to have one neuron for Bill, one for Samantha, one for Roger, one for Grace, one for Ellen. But rather with the distributed coding method, we could take different features associated with all of them, and they all may have similar features across all five objects, or all five faces in this particular case. But the pattern of firing of each one of our neurons, so here's neuron 1, neuron 2, and neuron 3, that pattern of firing ultimately is what makes us being able to identify Bill as Bill and Samantha as Samantha, not just having one single neuron that says this is Bill or this is Samantha. So again, that's very, very important for us to be able to understand that idea. And again, we do definitely see this also being replicated with primates in terms of a monkey's cortex that definitely do show that kind of distributing coding, rather than just having this specificity coding idea that we see. All right, that wraps up our discussion associated with Chapter 2, with the beginnings of perception. Please make sure to look on Blackboard under the information sheet for this week and complete anything that's being requested in terms of quizzes and discussion boards. And if you do have any questions or concerns, please feel free to email me or call, and I'll be happy to answer any questions. I hope you all enjoyed this week's lecture, and I'll be looking forward to presenting next week.